Okay, so what we're going to be doing now is moving forward with what we talked about last time. What did we talk about last time? Exactly, we talked about confidence intervals last time. And what is a confidence interval? Yeah, Michael?
Shows like how confident you are that the sample mean is the population.
Yeah, I mean, I get a little nervous when we talk about how confident we are because it sounds like it's like kind of an emotional state, but it's really a matter of probability. So if we are if there's 95% confidence, for example, that means there's a 95% chance that the true population mean lies within these parameters. It's like thematically the same thing, but you know, we get a little like nervous when we talk about it's emotional state, right? It's math, there are no emotions. So this goes a certain distance above and below what value? What's these distances we're going above and below? What do we add and subtract? The margin of error. And what is this value right here in the middle that we're adding and subtracting from? The mean. Also known as our point estimate. This is our point estimate. It is our best guess, for lack of a better word, our estimation as to what the true population parameter is. And then we build a confidence interval and say, well, it could be above and below this. Whenever you see polling data, they will usually give you a margin of error plus or minus 3 percentage points, plus or minus 2 percentage points. That's trying to construct usually 95%. But you know, you have to read the fine print to see exactly what confidence interval there's, or what confidence level they are saying. It was this x bar plus or minus the z-score, alpha divided by 2. Sometimes I like to put a little line between my z just so we don't think it's a 2. Sigma square root of n. Now, as we talked about, this equation is a little weird. We use this equation when we know sigma. But of course, in practice, knowing sigma is really hard. Why? Right? Exactly. The whole point of this is to figure out, to get a good estimation of mu. But in order to calculate sigma, we need mu. So it seems like weird. Now, as I mentioned, that could still be the case. Like maybe you have a lot of data on the population standard deviation from the past, and so it might be you might have reason to think that the mean has shifted when the population distribution is the same. That can happen. But generally speaking, we will often need to not rely on the true sigma. We will have to rely on something else when we don't know sigma, when we have an unknown sigma. What do you think is our estimate of our sigma? Yeah. S. Excellent. Like just as our best guess of mu is this point estimate is x bar, our best guess of sigma is S. And what is S? Well, you said S, so.
Sample standard deviation.
Exactly. If sigma is the population standard deviation, then naturally we use the sample standard deviation as the next best alternative. Here's where things get tricky. That sigma, if we know what the distribution looks like, then we can then normalize that distribution into the standard normal distribution with a mean of 0 and a standard deviation of 1. If we have a mean of 0 and a standard deviation of 1, if we get to use our standard normal distribution, we get to use z-scores. Z-scores are very precise amounts. 95%, 1.96, and so forth. If we don't know what this looks like, and we're relying on S, then that means how good that estimate is directly depends on a different variable. The variable that determines how much information we have. If you're working with only 5 observations, then that S estimate, that estimate of sigma, that S, is probably not as good as observations as when you have 50 observations or 100 observations. So we instead use something called the T distribution to capture that idea. We'll say T values instead of T values. The T distribution is really a family of distributions. It is a sort of normal distribution, but it changes shape based on how much information we have. As n increases, it begins to approach the standard normal distribution we know and love. We measure how much information we have, essentially, by degrees of freedom. Which is just equal to degrees of freedom equals n minus 1. So, anyone have any questions so far? No? Has anyone ever heard that term, degrees of freedom, before? Okay. Let me explain to you a little bit as to why it makes sense we take n and we subtract 1. Dennis, let's imagine that I am thinking of 3 numbers. I got 3 numbers in my head. And I'm going to tell you that the average of those 3 numbers is 6. Now, how many different combinations of numbers can I be thinking of? That would get an average of 6. Well, like, could I be thinking of 0, 6, and 12? Would that give us an average of 6? Could I be thinking of 0, 6, and 12? Yeah, that would give us an average of 6, right? Is that the only combination that I could be thinking of? How many combinations are there? How many different numbers, or how many combinations of numbers are there for me to be thinking of that gives me an average of 6? A lot. Can I be thinking of nothing but 6s? 6, 6, 6. Could I be thinking of 1, 10, and 7? Right. That would give me an average of 6. How many different combinations are there? There's a particular number I'm looking for. It's not really a number, but yeah. Infinite. Thank you. There's an infinite number of different combinations I can think of, right? That would get me, I can think of like, I'd be thinking of like 1,000,000 is one of them, and then maybe another one is like a negative, 100,000 or something, and then another one, so there are an infinite number of combinations. Let's imagine, though, that I tell you I am working, one of my numbers is 4. Are there still an infinite number of combinations? Yeah, there still are. Right, absolutely. What if I tell you my other number is 0? Are there an infinite number of combinations? No. What number am I, can you tell me what number I'm thinking of then? How do you know? 14, yeah. Exactly. Right. So in other words, I'm thinking of three numbers. Two of those can vary in a number of ways, but when those two numbers are locked down, the third one has to be locked down as well, because I know the average. Is everyone with me so far? Logically, do you see how this connects? Right. That's the story here. The idea is, whenever you're working with it, you know the average, right? You know the sample average, right? This is what you're trying to estimate. So that number is locked down. And then the number of ways anything can vary is based on the number of observations minus 1. Two numbers can vary, but no matter what numbers you end up with, the third one has to be locked down. So these two can be anything, and then there's only one answer for the last one. So that's why we take n minus 1, because we know the average, and therefore everything else has to change. Everything else can change except for one of the other variables. Are we good? Right. Just trying to get you to understand why we subtract 1. That's why, because we know the average. So here is a plot of the t-distribution. This is a family distribution. We're using b in order to rather than df, but the basic idea is the same. This yellow line right here, that yellow line represents 1 degree of freedom, right? There's a sample size of 2, it's 1 degree of freedom. Note that it's pretty flat. This black line right here represents our standard normal distribution. So note that when we only have 1 degree of freedom, we know less. The tails are fatter, they go out a bit more, and then the peak is smaller, the kurtosis is negative. And then as we get more information, going from 1 degree of freedom to 2 degrees of freedom to 5 degrees of freedom, we begin to know more and more, and it begins to approach our normal distribution. In other words, this is essentially statistics' way of covering our butt. Like, okay, we have less information. We're going to reflect the fact that we have less information by saying the distribution is a bit more spread out than normal. And so as a result, the t-scores that we use are going to be a little bit higher. That's the short version of this. The t-scores we use, rather than the z-scores, which are fixed. That 95% confidence means 1.96 z-score. The t at 95% confidence is going to change based on how many degrees of freedom we have. And the more degrees of freedom we have, the closer it'll be to 1.96. Any questions so far? Great. In the days of yore, before computers, or at least before Excel, or maybe in classes where you don't have Excel and you have to do this by hand, if you wanted to know a t-distribution, if you want to know a t-value, you had to look it up on a table. For some reason, there it is. Now it goes. This is this table. This table is a giant pain in the ass. Because rather than having just those like 3 numbers I gave you, you have thousands of hundreds, probably thousands, theoretically thousands. This is certainly hundreds of numbers. So if you have, 10 degrees of freedom, and then you had to see, okay, what is my, how many observations do I, let's say, what is my confidence level, what is my alpha, you would have to look it up on the table, and then you would find it. That's really annoying. The good news is Excel has this entire table built into it. And so we can use Excel to figure out what our critical value should be. So open up an Excel for me, please, just any blank one. While that's loading up, let me give you the equation we will be using instead. X bar is the same, plus or minus t alpha divided by 2. Again, that t sub alpha divided by 2 is one variable and one variable only. We multiply it by S instead of sigma, and then we divide by square root of n as normal. So we can learn about any of this. I want to show you how this works. So if you could go ahead and type df for that, for our degrees of freedom, and then our crit values. And we'll go, I don't know, let's go 1 degree, 5 degrees, 10 degrees. I don't know, let's do 15 and 20 and 30 and 50 and I don't know, like a whole bunch. There we go. Zoom out a little bit. Now, when you recall how we found out what our critical values were when we were working with z-values. Do you recall how we did that? Right. So we used that norm invert function, right? Well, Excel has a similar function in it. It has a t invert function, and it has a t invert 2t. That 2t means anyone? Two tails. Right. So you can immediately take that, you know how we, as Amanda points out, we took that alpha divided by 2 for the norm distribution. This will do that automatically. And t invert just looks at this area. T invert 2t takes out alpha, divides it by 2, and sticks on either side. This value will always come out positive. This value will come out positive or negative depending on where you're going. Any questions? Yeah?
So how many when we just asked for
Well, what we're going to be doing a lot next class is talking about when to use 1 or 2 tails. For our purposes, though, for confidence intervals, they always use 2 tails. That's why alpha is divided by 2, because you're going in 2 different directions. So I'm going to start with t invert, and you see our I and V and our I and V 2t. So let's use the 2-tail test. The probability we'll set at 95% or 0.05. Oops. Comma, and then we'll select degrees of freedom. And you get a huge value, which should not surprise us at all. If you're working with only 2 observations and you want to claim that you're capturing the true population mean, you're going to have to take 12.7, put it right in this value, and then it's going to be huge, right? I mean, it's going to be huge. They have to multiply it by the standard deviation and then take it divided by the square root of 2. That's going to be a very big range. But it should be a big range. You're operating on only 2 observations, right? You know very little. Yeah. I just referenced that A2. Now appreciate too the symmetry between what we just did and the other way we could do it, the way that we did it with a normal distribution. If we did t invert and we did 0.05 divided by 2, comma 1 degree of freedom, we did literally the same thing. You will note this will be a negative value because it's going to go to the left because we're looking at 1 tail. We're looking at the 5% on the left. But otherwise, it's exactly the same result.
Oh, I'm sorry.
Oh, okay. So again, this is what Excel is doing when it's using the t invert 2t, is it's taking alpha that you put in, dividing it by 2, and then taking the absolute value. It's literally the same thing. Yeah. Yeah, I just put in 1 rather than A2, but it's the same thing. I'm just showing you that they're the same thing. Showing you how these 2 seemingly similar commands can be treated as the same and how exactly they're different.
So all the difference is divided.
Yeah, essentially. And take the absolute value. Because T2 represents something closer to distance. Or I'm sorry, 2T. 2T is something closer to distance. Okay, what do you think will happen when I copy and paste that critical value? And hell, we'll even indicate it's critical value 95%. We'll say 95% confidence. Now we'll just make it clear. What do you think will happen when I copy and paste this down? And get T values for all of these possibilities? What will happen to that 95% confidence T value? Remember, as we get more degrees of freedom, the T distribution approaches the Z distribution, or the normal distribution. And as the T distribution approaches the normal distribution, then we can essentially not have to be so concerned about we have this really weird sample. Right? That our estimation of S really is close to sigma. It's better if you can use sigma, because sigma gives you a better estimate of that normal distribution. But in practice, you often have to use S, and which means you have to use T values. So those critical values are going to be higher, which results in a wider confidence interval. But note, as we get a ridiculous number of degrees of freedom here at the bottom, when we get a ridiculous number of degrees of freedom, this is 10 million degrees of freedom, then this is functionally the same as our Z-score for 95% confidence. This is 1.96. Because if you have like 10 million observations, I'm sorry, 10 million one observations, because it's degrees of freedom. If you have 10 million one observations, and you estimate the standard deviation as S, it's like, well, that's probably sigma. This sigma is probably the same. Any questions? So I'm going to set up bias sampler. Okay. Now, it turns out that Excel also has our confidence equation built into it. And whenever you don't know how to do something in Excel, what do? That's right. Note that we will not be selecting confidence norm. We will select confidence T. Note that confidence T is asking for familiar things, just like confidence norm does. It's asking for alpha, or 1 minus our confidence level. It's asking for standard deviation, just like before. It's asking for size. What is size? Also known as what letter? N. S is standard deviation. N. So it's asking for a lot of the same stuff. Let's put that stuff in. 0.05. We'll say, let's imagine we have a standard deviation of 5. Oh no, let's make it 6 just to make it different. Because I don't want to have two 5s. So 0.05, 6, and we'll say, it's coming up. There we go, 10. You hit enter. There it is. Note how different that is compared to if we were to do the same thing. Confidence norm, alpha 0.05, standard deviation of 5, size of 10. I'm sorry, standard deviation of 6, size of 10. It's a little bit smaller. It's a little bit smaller because we have less information in this one, and it's 4.29 than we do here in 3.7. There's a big difference between knowing, oh, you want to show formulas? There's a big difference between knowing sigma and not knowing sigma. Oh, sorry. I mean, it's the same thing. It's the same input, just different command, yeah. the confidence norm function only will calculate this part right here. Or, here, let's do it. Confidence norm confidence T only do the margin of error. Because all confidence intervals needs two numbers. And so it's outputting one number. Any questions? We can appreciate it did exactly the same thing that we told it to. Just to unpack this a little bit. Because if I put in equals t invert 2t 0.05, we had 10 observations, so that means we have 9 degrees of freedom. Multiply it by 6, divide by the square root of 10. We get the same thing. So confidence T does what I did on the board. It's exactly the same thing. But it's helpful because now that we've seen it, we can see as we get, say, more information, as we increase our sample size, confidence T goes down. It gets narrower. The margin of error decreases. It decreases not just because n is directly included in the equation. It also decreases because increasing n increases the degrees of freedom and decreases T. So increasing n is doubly effective when you are working with an unknown standard, unknown sigma, an unknown population standard deviation. None of what I've talked about here applies to the kind of polling we're seeing a lot because it's an election year. All that polling is based on percents, and percents have bounds. What's the lowest a percent can be? 0. What's the highest it can be? 100. And that changes our math. So we instead rely on a different confidence interval for proportion. CI or proportion. I go into a bunch of details in the notes about how this is calculated and the logic behind it, but let's just start with the equation. So we begin with P bar. P bar is X bar, but it is our estimated average of the proportion. It's our sample average, essentially. We're going to do plus and minus again, just like before. We have to because we're making a confidence interval. Because of the nature of proportions, they're bounded reality, then we can use z-scores. You can pretty accurately calculate the sigma for proportions as just a matter of the population. I include the equation in your notes. But like I said, we're not going to get really too far into it. Just safe to say, we can use these scores here. We will then use the square root function for the whole thing, not just for n. And the denominator is n. And then the numerator is, well, I guess we use that. That's fine. P bar, 1 minus P bar. This up here, these confidence intervals are used to estimate mu. Confidence interval for proportion is used to estimate pi. Let me emphasize, and I will say this multiple times, this is not 3.1415926535787. It is not the estimation of the ratio between the length and the diameter of a circle, or the circumference and diameter of a circle. This is a variable. Just like we like using Greek letters for population values, like mu and sigma, this is our Greek letter for the population proportion. We are trying to estimate this. Yeah. So we're trying to estimate the population proportion. No. I know, it's kind of weird. We don't ever use P. Well, I mean, so in some cases you might use P just like you might use X. You know, we have absolute X bar. You might use P as a particular observation. But, and for now we're just going to use P bar, and I don't know, maybe they want to harmonize it with X bar. Any questions, by the way, on this logic? Okay, we'll do an example in a moment, but any questions on this logic? No. One of the reasons this is set up this way we can use Z is because this equation creates a natural bound. So appreciate the symmetry between this and this. This is our estimate of the standard deviation of that population proportion. And because it is bounded between 0 and 1, there is a bound to how big that standard deviation is. Like, you can't have a standard deviation of 20 when you're only between 0 and 1. It does not make sense. Because of the math of how this works, that means we can estimate what that bound is. What do you think the highest value this can be? Like, what P bar value will make the numerator as big as it can possibly be? Yeah? Yeah. I don't know. It has to be 0.5. Why? Exactly. And we can show this. Oops. Let me highlight and scroll down, and we'll do like to 0.9. And we'll do this equals that value times 1 minus that value. The largest it ever gets is 0.25.
This is why we get to use these scores, essentially. And so sometimes if you really want a conservative analysis,
If you really want to approach this in a very conservative way, you can have a p-value for this, but then if you want to make this as large as you want, as long as you can, just to be as cautious as you possibly can, you make these values 0.5. Let's go through an example then. Let's say we're trying to figure out polling data. Let's imagine that a particular candidate has a, we do a whole sample and we get a p-bar of 30%. They have 30% support. Let's imagine we ask, I don't know, let's say 1,000 voters. And let's get a z-value of 95% confidence. Oops. So I guess we'll do, so at 95% confidence, what is our z-value? That would be our alpha. 0.5 is our alpha. What is our z-value? .96. So our margin of error is equal to, how do we do this? We got like 2 minutes, we got like a minute left basically. How do we do this?
Follow the equation. That's a cool equation I hate for you. Remember, we are trying to estimate our margin of error. So we first take it and multiply it by 1. We take 1.96 as we score. We multiply it by what? Anyone?
We need a square root. So XQRT is our square root function in Excel. And then what do we do? 0.3 times 1 minus 0.3 divided by, yep. And of course, because I put in all cell references, I can change everything and we can change how things go. And so we have plus or minus 2.8 percentage points. Note I said percentage points. Do not say percent, because 2.8% of 30% is 0.3 times 0.228. Oops. Is that, right? That is 2.8% of 30% is 0.08. You see, it's confusing. Talk in terms of percentage points. 2.8 percentage points. So I might, as abbreviate, we might say plus or minus 2.8%, but we mean percentage points. So you look damn foolish. And now, of course, if you want, you can see how much this changes. If I only ask 100 people, it gets a lot bigger, 9 percentage points. Yeah. Yep, sure will. But you see, it's exactly the same as this right here. And with that in mind, so no more questions, I will let you go. Have a great couple of days, everyone. I will see you next time.